Good morning. This is your video for section 5.4, use medians and altitudes. We're going to start out with the definition of a median of a triangle. I think you should write this in your notes, so you should pause the video, copy down the definition of the median. It's a segment from a vertex to the midpoint of the opposite side. So I have a blue triangle down here, and I'm going to draw the medians. So let's go from this vertex to this opposite side. And it said it goes to the midpoint of the opposite side. So I'm going to try to just look at it and see if I can, maybe right there. Looks like the midpoint. So the median is from there to there. And to show it's the midpoint of that side, I do the tick marks. So that is a median. And then here we have the medians of a triangle are concurrent, and the point of concurrency is called the centroid. So I'm going to draw another triangle, and I'm going to sketch all three medians. So for this angle, we'll say we go right there to the midpoint. There's one median. For this angle, looks like that's the midpoint, so I'll sketch that median. And for this angle right here, we're going to go to that midpoint, and we'll sketch that median. And if we call that point of concurrency P, we would say P is a centroid. That's our third point of concurrency. Now we have theorem 5.8. It says the medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So there's a lot going on right there. First off, we need to sketch all three medians. And I'll have to use the big dot theorem. So let's call this ABC. And the centroid P. And we're actually going to name all these little midpoints of each side too, D, E, F. So this theorem says the medians of a triangle intersect at a point. That point is P. It is the centroid. That is 2/3 of the distance from each vertex to the midpoint of the opposite side. So that's our equation we're going to use. It's going to be the centroid equals 2/3 of means multiply the distance from the vertex to the centroid. Let's see, I need to look at that. No, that's not quite right. Sorry about that. If there was a way to back up on the recording, I would have done it. Okay, sorry about that. I've got it straight now. So from the vertex to the centroid, that is 2/3 of the entire median. So if we look at median AE, from A to P, vertex to the centroid, that is 2/3 of the entire median AE. So if we can make this a little larger, from here to here is 2/3 of the whole thing. Well, if that part is 2/3, then how much is left for this part right here? 1/3, because the whole thing would be 3/3. Okay, here's an example of where we're going to use that statement. And I didn't tell you to do so, but I think you should bubble this. This is the important statement for this section. This is going to be the key to getting all these homework problems right. So I think you should bubble that. Alrighty, so we have a triangle here, and it says Q is the centroid. And it tells us that SQ is 8. Alrighty, I'm going to make it just a little bit larger. So we just wrote down from the vertex to the centroid is 2/3 of the entire median. So right here, S to Q, that's vertex to centroid. That's the 2/3 part. Well, do you know what 1/3 would be? If 2/3 are 8, do you know what 1/3 would be? Well, it'd be half of 2/3, so it'd be half of 8. So 1/3 would be 4. But if you wanted to work it out with algebra, from the vertex to the centroid, that's 8 units long. That equals 2/3 of the entire thing. I'll just call that 2/3 of SW. And then we can clear this 2/3. We will probably multiply by 3 on both sides. That's 3 cancels out, and it's 2 times SW. And then we'll divide both sides by 2. So 12 equals SW. So that just helped us to find that the whole thing was 12. And so if this portion of it was 8, 12 minus 8 leaves us with 4. So QW is 4 and SW is 12. So you can think about it different ways. Okay, I feel like you probably need another example. So it says E is the centroid, so we automatically know those other segments that are drawn are medians. They want us to find CE if ED is 6. So we know from the vertex, the thing we bubbled, to the centroid is 2/3 of the entire median. Well, vertex to centroid, here's the vertex, here is the centroid, so we're talking about that section right there. CE is 2/3 of the entire median, so this is the 2/3 part of the entire median. CD, that doesn't help me very much. Let's go back to just the very basic. We just said that was 2/3. So how much is left for this piece? 1/3. So 6 is 1/3. How much is 2/3? Well, it'd be 12. If 1/3 is 6, then 2 of those would be 12. So then we know that CE is 12. So I guess we don't really have to use too much of that thing right there. They wanted us to find CE. CE is 12. And how long would CD be? The entire median? Well, it'd be 12 plus 6, 18. Okay, now we're going to talk about an altitude. I think you should pause the video and write down this definition. The altitude of a triangle is the perpendicular segment from the vertex to the opposite side, or the line that contains the opposite side. We'll talk about that part in just a second. So let's talk about this vertex right here. It's the perpendicular segment from this vertex to this opposite side. So all we do is we say we drop a perpendicular. You want to make a segment so that you got a right angle right there, and that's your altitude. What if we wanted to draw the altitude from that vertex to this opposite side? Well, I can't drop a perpendicular to that opposite side. So that's where this, the line that contains the opposite side comes in. Well, this side is a part of a line. Sorry, it's a little messy. Part of a line here. So we can take the altitude, we can drop it from the vertex to the line that contains the opposite side, and that's the altitude. So yes, the altitude can be outside of the triangle. What if I want the altitude from this vertex to its opposite side? Oh, and I forgot to tell you, this is already a right triangle. Well, if I need the perpendicular from this vertex to this opposite side, it's actually that side right there. That side is the altitude. And triangles have 3 altitudes. The altitudes of a triangle are concurrent. The point of concurrency is called the orthocenter. When we are back together again on Tuesday, we will talk about a way to try to match up these special segments and their points of concurrency. I was just thinking possibly we might want to draw all the altitudes for these triangles. So the altitude that goes from this vertex would be right here, and the altitude from this vertex would be right there, and they should be concurrent. The altitude from this vertex to the line that contains this side would actually be out here like this, and the altitude from this vertex to that side would be right there. And if I extend these out, because they are lines, whoa, sorry about that. Oh, I must have some of these a little crooked. Let's try again. Let's actually use the line tool. There's one of them is still kind of off. I'll cheat just a little bit and say there's my orthocenter. Here's the orthocenter. It's inside the triangle, and on the acute triangle. On the obtuse triangle, it's outside the triangle. Remember, this was the original triangle right here. And for the right triangle, for this vertex, that's an altitude. For this vertex, that's an altitude. And for this vertex, this is an altitude. And they all 3 cross right there. If you let them all continue. There's your orthocenter. And just kind of cool. The orthocenter doesn't actually have a property that we have to work out like we did for the median. So there's not an example to go with it. That's it for today.